Hi there, and welcome to GTC for 2023. My name is Steve Ulrich, and I'll be presenting today with my co-presenter, Aurélien Chartier. We both work for the DevTools group at NVIDIA, and our specialty is the CUDA correctness tools. So today I'd like to spend about the first 20 plus minutes talking about the correctness tools for debugging. Then I'll hand off my presentation to Aurélien, who will talk about the sanitizer correctness tools. So when I'm talking about the debugging tools, we're going to cover this with an overview. And under the overview, I just want to talk about the suite of tools and how they're related to each other. And then once we've talked about the overview and given you a little background information, we'll talk about CUDA GDB. Those might be familiar with it, and we'll save the details for when we actually get into the discussion. And then we'll talk about three different Nsight visual tools, the Nsight Visual Studio Edition, Nsight Visual Studio Code Edition, and then lastly, Nsight Eclipse Edition, three different IDE tools that we use to provide IDE integrated build and debug support for CUDA. So when we talk about the tools, we group them really into three different categories. We have command line tools, and the command line tools are going to be CUDA GDB, which works under Linux and provides both CPU and GPU debug support of CUDA applications. Additionally, in the command line tools for our correctness, we have our sanitizer. Sanitizer works on both Windows and Linux and provides a second level of correctness support above and beyond traditional debugging correctness. I'll be covering the debug tools, and like I mentioned, Aurélien will be covering the sanitizer tool. When we split off into the other category, we talk about our IDE tools. We have Nsight Eclipse Edition, which runs on Linux and supports build and debug standard IDE services for integrated development. It is a Linux-based tool as far as how we support it at NVIDIA, because we support Linux-based local development and then various types of remote development, all to various flavors of non-Windows targets. We also have Nsight Visual Studio Edition, Windows only, and that is an environment we use for doing CUDA development on Windows, both build and debug support. A recent addition to our portfolio is Nsight Visual Studio Code Edition. And for those who've been getting used to Visual Studio Code, it does run on Windows and ARM. However, because of the way we've layered it, Visual Studio Code Edition, we really use it primarily as a Linux-based tool. Now, all of these tools, our command line tools and our IDE tools, are layered on top of developer libraries. For the debugger side, we offer the CUDA Debugger API for our Linux-based development. We have an internal version for Windows, but when we talk about external support and something that is available for third-party development, you can get a copy of the Debugger API and use it if you wanted to write your own debugger or do your own direct development. Additionally, we have a sanitizer API. Likewise is the API which is supported if you want to do your own development within the tool framework of what type of correctness tools are offered by Sanitizer. That's the overview, and now we'd like to spend a little time covering each one of the tools in a little bit more detail. Let's talk about debugging. When you're doing your debugging, you're really saying that you want to have a window onto what's going on inside your code while it's running on the CPU and the GPU. And debugger really is only as good as the metadata that is provided by the compiler. You know, if you're trying to debug code and you've just got a bunch of bits on the system, you really can't get much useful information out of it. So we need to help the compiler to give us the correctness information so that a debugger can do a good job. So we have to tell the compiler we're going to compile for CPU debugging or GPU debugging or both. We use the traditional lowercase -g to tell the compiler we're going to do CPU debugging. We've extended that, and for GPU debugging, we have the uppercase G. When we do that, the compiler makes a number of changes to the way it generates code. It inserts metadata, first of all, into the executable to guide the debugger. It'll tell us things like, where is this local variable going to be found? Is it in a register? Is it on the stack? Where can we look for it so that we can present it in the user interface? Additionally, there's information of how do you get from the current stack all the way back up to the parent, recursively traversing some sort of a call graph. Those are the primary bits of metadata that we need so that we can present a clean view of the state of the machine in a human readable form. Now, side effects of this. When we turn on -G, the compiler is not going to generate the same efficient code. Readable code and optimized code are simply fundamentally different, and we trade off performance when we're doing correctness validation. So you're going to get lower runtime performance. Additionally, if you're looking at the disassembly, because the code is not intended to be as optimal as humanly possible, it's going to be very readable, but it's going to have redundant loads, stores. It won't look like something that is designed to be effective. But we end up trading off all of these modifications we make so that we can give the debugger enough information to present the information. Now let's move on to the actual tools themselves. We'll start with CUDA GDB. CUDA GDB is built on the familiar GDB debugger that's been around for, I think, going on 4 decades. If you're used to debugging on Linux, you're used to GDB. We provide a very similar experience. We support C, C++, Fortran, and because we've integrated into GDB, we treat CPU debug and GPU debug identically. You can get a breakpoint and you can look at either environment and you will be basically looking like you're doing source level debugging regardless of if you're debugging CPU side or GPU side. We do support CUDA, we have support for optics, and for other types of development of code that runs on the GPU. GDB supports SAS disassembly and has a number of unique extensions to make development in CUDA very easy. We'll talk about the details a little bit more as we get further into the presentation. We also, within GDB, support core dumps. So if you don't want to actually start your program in the GDB, you can run it, and if an exception happens or if you force a core dump, you can bring that core dump into GDB and have a look. We are doing the best we can within NVIDIA to stay up to date with the GDB releases. Our current CUDA GDB is based upon GDB 12.1. As people might be aware, GDB has recently announced 13.1, and we have a development effort happening now to catch GDB up to the 13.1 GDB release, which just came out a few days ago. All of the source code is available on GitHub. We are clean according to open source principles. So if you go there, you can see the GDB sources and look at the deltas that we make to make CUDA GDB support exist. CUDA GDB runs primarily on Linux. We support all of the distros that the CUDA toolkit runs: CentOS, Fedora, Red Hat, Ubuntu. We've recently added support for Windows WSL2 as well. So if you want to do GDB-based debugging on Windows in the WSL2 framework, we provide good support there. We do have a version of GDB that runs on the Mac, though with a caveat that that is host support only. For those who are used to using GDB and GDB server to do local host and remote target, the Mac supports that dual model with CUDA GDB server on the remote end, but we don't support direct debugging on a Mac. So if we're thinking about GDB, there's really 2 fundamental ways to start. You can, if you look at the upper left, you can do CUDA GDB and run your application, just like GDB has been used for 4 decades. You bring in your application, it reads the symbols, you run, and you'll either run to an exception, or you can run and Control C and then inspect your control. If you don't want to start GDB or start your program under GDB, you can also start your program all by itself, get the process ID, and then at some later date, you can attach to that process ID. Once you're there, you are in a position where the program has been stopped and you can resume execution, or you can use various commands to inspect the state of the running program. If you quit, an application that has been started with run will be killed. And if you have attached and you quit, you'll detach. Very, very traditional, two useful ways. Sometimes it can be quite advantageous to do an attach because there is a performance overhead when you run with CUDA GDB. It might be easier to run your program for a while, get to a point where you know you need to debug it, then attach so that that performance overhead is reduced. Within CUDA GDB, we've extended it with various CUDA commands to provide CUDA level control of your debugging. Things you're used to when you're doing CUDA development, obviously this is a highly parallel environment. And so we provide CUDA commands for things like devices, the SMs, your warps, your lanes, kernels, contexts, etc. All of these idioms of the CUDA programming environment are available to you through CUDA commands. So you can use info CUDA to do queries, and you can use other CUDA commands to change your focus so that you can look around and debug the threads of your CUDA program that are of interest. Continuing. As I mentioned, GDB only ever presents a single thread of focus at a time. And we've extended that model in CUDA GDB. So at any one moment in time, when the debugger is stopped, a single thread is of interest. If you do a backtrace, you'll get the thread of execution for that thread only. So we provide a number of different CUDA commands to change your focus. And we provide various levels of control there. So you can specify just a given thread within the current subcontext, or blocks and threads, or all the way up to a specific kernel, full block addressing, full thread addressing. But the underlying issue and the thing to bear in mind there is you always have a current thread of execution, and you are always inspecting your state within that thread of execution. As I mentioned, within CUDA GDB, we have full disassembly support. Now, within CUDA GDB, when you do your disassembly, you are seeing SAS instructions. Now, there is another form of CUDA disassembly called PTX. However, CUDA GDB only works within the SAS domain. When we talk a little bit later about some of our other tools, we'll show the extensions we have for PTX. Now, one useful feature of the disassembly is that we distinguish the program counter at which the program is currently running, and we distinguish that from any program counter which might be associated with an exception that had happened and maybe stopped your program. Since we do allow program counters to proceed forward as long as there are no dependencies on the, for example, a load that was required, we can have some distance between the program counter that generated an exception and the program counter that's currently executing. So we distinguish the exception program counter with a prefix of a star greater than symbol compared to the current program counter, which is an equal to greater than. If you look at these two listings, the top one shows the current program counter. The lower one actually shows that the error occurred a few instructions prior. So when you're doing low-level debugging and trying to find out exactly what might have triggered a failure, looking at the error PC is a useful way to make sure you know exactly what line of code is causing the problem. As I mentioned, we support core dumps. Core dumps are a feature of GDB, but they're also a feature of the CUDA runtime. So what you'll want to do if you want to do core dumps is you'll actually enable them by setting an environment variable, CUDA enable core dump on exception. You'll set that to 1. And if you set that environment variable and run your program and it takes an exception, you'll get a core dump. and you can load that core dump into GDB and inspect your state. There are some useful characteristics that you can provide there for defining your core dump name. You can set the process ID, the time, the host name, and this is a useful way so that you can make sure you associate your core dump with a specific runtime. And especially in large environments where you're running lots of different processes on some sort of a shared system, being able to identify your core dump and distinguish it using this core dump naming can be a very useful feature. As I mentioned, when you're running a CUDA program and you have a system that has multiple GPUs, CUDA can take advantage of all of those GPUs. So if you have a system with 2 Pascals and 2 amperes, your CUDA program can span all of these cards. So when we're debugging a program like that and you hit a breakpoint, it will stop all of the GPUs that are running CUDA. Now you can use the info CUDA kernels command to list all the active kernels. And you can switch back and forth with the CUDA kernel command to switch between the various kernels. So it's very important to remember that you're debugging all of the GPUs that are active, and you'll stop all of them at a breakpoint. If you want to reduce that and actually have a finer grained set of GPUs that are participating in your CUDA program, you can always use the environment variable CUDA visible devices. You can set that as a pattern to restrict the number of GPUs which are visible to the CUDA runtime, and consequently, they will not be visible to CUDA GDB during debugging. Very recently, within about the last year, we've extended our CUDA GDB support to include support for GDB's Python interpreter. It's a really cool feature, and if you want to bring in Python as shown in the example at the bottom, you end up with a GDB module that you can use to do things like evaluating expressions or looking at a specific value, and then you can do that within a larger Python program. So this example here actually searches from a range from 0 to 316 and is looking for a specific program counter range. Very useful and as a way to extend GDB so that you can actually have programmatic support of your debugging for sophisticated debugging usages. Now, some caveats. GDB support for Python is a little bit strict. We build against Python 3.6. We open it with DLOpen. And if your version of Python has a different binary interface than Python 3.6, there could be some glitches. We currently do a build once, run anywhere environment with CUDA GDB. And so if your version of GDB doesn't work, you might not want to use Python, and you can disable it by setting disable Python on the command line. We're planning to have support for a more robust Python interface in the second half of this year so that regardless of your distro, you'll be able to have Python support. I mentioned that we have WSL2 support. That is available on Pascal through Ampere architectures. At the time that we started our WSL2 support, we were making a transition from one architectural backend to a different architectural backend. And that new architecture, which is supporting Ada and Hopper, is one that hasn't yet been ported over for our WSL2 support. We're anticipating extending our support for architectures all the way Pascal through Hopper in the second half of this year. Right. Now that we've talked about CUDA GDB, let's switch gears and talk about Insight Visual Studio Edition. NVIDIA has added extension support for Microsoft's Visual Studio. To do that, we have added support for Visual Studio 2017, 2019, and 2022. Now, for those who are keeping track, as of Visual Studio 2022, 64-bit program support has been included. So 2022 is really a great IDE for debugging large CUDA programs. So if you've got a CUDA program consuming more than 4 gigabytes of RAM, using 2022 is the right IDE so that you can get full support for that larger memory footprint. Now, because we support that larger memory footprint, we took one trade-off, and we do not support the Maxwell architecture inside 2022. This is because of the way we have done the various architectural support and the extensions for all of these different debugger backends. You can do Maxwell in 2017 and 2019, but if you're doing Maxwell, stay in the lower ones, and for Pascal Plus, you can use 2022. As with all of the other supports we're providing, we can provide CUDA C, C++, and seamless GPU and CPU debugging. Visual Studio provides SAS disassembly and also PTX disassembly, and if you're interested, a hybrid mix of both SAS and PTX interleaved. Now, one killer feature we have in our CUDA support in Insight Visual Studio Edition is we do support GPU evaluated conditions. For Linux, we support various types of conditional breakpoints, but they're evaluated after stopping the GPU and inspecting the program state. The conditions we evaluate in Visual Studio are evaluated on the GPU, and so they run dramatically faster. A caveat to that is we've implemented these conditional breakpoints with a microcompiler inside of our support, and we have a limited number of registers to implement these expressions. So if for a really complicated expression, something that might have 10 terms, we could break and we won't be able to actually do that. But for any normal type of condition, like identifying the thread of execution that you're trying to match, we have full support and we have GPU evaluated conditions, so they run at very high speed. Here we're showing a screen grab from running a CUDA debug session inside Insight Visual Studio Edition. If you look, you can see matrixmul.cu source code and the traditional red circles representing debugger breakpoints and yellow showing an hit breakpoint. You can see in the lower right that we have a traditional breakpoint window. It's the same breakpoint window for CPU and GPU. We show local variables in the lower left. And in the top left, you can see GPU registers. Again, a seamless debugging environment, whether you're debugging on the CPU side or the GPU side. As I mentioned, we have a disassembly view. And if you look in the upper right, you can choose whether or not you want to look at the SAS, the PTX, or even a merged version to show both the PTX instruction and the SAS instructions. So disassembly support is very, very well supported and is a nice seamless integration for your CUDA debugging. I mentioned we have conditional breakpoints. The conditional breakpoints look exactly like the way you'd set conditional breakpoints on the CPU side. You can right-click on the well-known red circles that we have for breakpoints. It brings up the interface. And you can see here this specific conditional breakpoint is set for when thread idx.x is 3 and thread idx.y is 7. So if you have a CUDA program where only certain threads are crashing, you can actually set a conditional breakpoint here and get to it quite quickly. I will offer a caveat. We do expression support with basically what amounts to a microcompiler inside of Visual Studio. We have a limited number of registers, and for very complicated expressions, there's a chance that that register set will be filled. We can't necessarily do all expressions, but for all reasonable expressions you'd want to set here, we expect we have enough support for it to work. Like I mentioned, lots of different windows to show the status of your program. Warp info is something we like to give you sort of a 30,000-foot view. What are your warps doing? It sort of gives you a top-down view of your GPU to give you a sense of what threads are executing, what are stopped, and sort of gives you a graphical picture of the throughput you're getting on your CUDA program. As I mentioned, we have two different backends for our architecture support. We have, in the debugger team, written a unified debugger backend, but because of some architectural differences, we only support Pascal and forward, Pascal all the way through Hopper on this unified backend. Visual Studio 2022 uses that and has the full Pascal through Hopper support. If you're doing legacy support, that's our Maxwell legacy architecture. It works fine. We still support it, but right now those are treated distinctly in Visual Studio. Switching over, as I mentioned, we have recently added support for Visual Studio Code. We've taken Microsoft Visual Studio Code and we've added extensions to it to provide seamless CUDA debugging support. Now, unlike Visual Studio, we've actually layered Visual Studio Code on top of CUDA GDB. So in the true sense of Visual Studio Code being an IDE, the underlying support is actually supported by CUDA GDB. So all of the quality that's built into CUDA GDB is brought forward, and Visual Studio Code presents a visualization of that information you're getting from CUDA GDB. We have two primary vectors of support that we're doing there. We have our CUDA language support, IntelliSense, syntax hiding, the problem matcher that you normally expect from any language support in Visual Studio Code. And then the full C, C++, CPU, and GPU debugging that you get from GDB. A screenshot. Again, we're using matrix mul. We see in the upper right that we have a breakpoint that's set. Down in the lower right, you're seeing the traditional problem space, the terminal, the debug console. So you can see sort of the communication that's happening back and forth between Visual Studio Code and the backend. We do the register views, local variables, call stacks. Just like a traditional IDE, all of these interfaces are seamlessly provided. Now, if you look in the lower right corner, you'll actually see that we have basically the index information for the current thread of execution. You can, inside Visual Studio Code, change your thread of execution by typing your specific thread of interest that you want to access, and we switch over and present that thread. So full IDE, but with CUDA GDB under the hood. As I mentioned, this is installed by extensions. So you can go to the Visual Studio Marketplace and you'd want to download Microsoft's C, C++ extension, and then the Inside Visual Studio Code Edition extension, and then you're up and running with Visual Studio Code. If you want to instead, you can go to the download page at developer.nvidia.com and download the extensions through that method and get the physics files that you can download directly. Do note that the installer is decoupled from Visual Studio Code and our CUDA toolkit. Since we depend upon CUDA GDB, even if you install all these plugins, you still need to install the toolkit. So you want to install the toolkit, install this, and you're up and running. As I mentioned, Insight Visual Studio Code Edition comes in two extensions. These are installed via the extensions interface inside Visual Studio Code, and they come from the Visual Studio Marketplace. You can get the C, C++ extension from Microsoft, which has integrated support for CUDA. You can also get the Insight Visual Studio Code Edition, which has all of the interconnects to connect Visual Studio Code to CUDA GDB. You can also get these via download if you want to get the physics files directly from developer.nvidia.com. Note here that these installers are decoupled. If you install these two extensions, you will get Visual Studio Code support, but you need an underlying toolkit to actually do CUDA development. So you'll want to install both of these extensions to support Visual Studio Code, but you'll need to install the toolkit to bring in the compilers and debugger that are necessary for actually doing CUDA development. So we'll talk briefly about Insight Eclipse Edition. Like Visual Studio Code, this is layered on top of CUDA GDB. It's another IDE that you can use for editing, build, and debug of CUDA application. We support this similar to Visual Studio Code in that we provide plugins, and you load in the plugins into your own Eclipse environment. We support Java 8 and Java 11, depending on the Eclipse version that you want to download. And because we do integrated builds, we also support cross-compilation. So while you can run this on x86, you can also do cross-development for Linux for Tegra, Drive Linux, Drive QNX. We are similarly adding support for cross-compilation to Visual Studio Code. That hasn't been released. It'll be released in the second half of this year. So if you're looking about Eclipse, you're looking at a full IDE for both the local development and also cross-development for our cross architectures. Traditional screenshot, we love matrix mul. You're seeing stack frames on the left, source code, and you can see the tabs for variables, breakpoints, expressions, and CUDA unique displays that are available on the tab. Very traditional. IDE support has been around for a while, and we provide a very clean, seamless interface for your Eclipse development. As I mentioned, inside Eclipse Edition plugins are shipped with a CUDA toolkit and are available for down or for installation. You can navigate, as I've shown here, to user local and your CUDA directory, Nsight EE plugins, and the extensions are available for install. So for any given install, you can find them in that subdirectory available with your CUDA toolkit. We support Java 8 for those who are used to the Java 8 environment. We test that for Eclipse 4.16. We have previously supported versions 4.9 through 4.15. They probably will work, but are no longer tested. If you've migrated to a more modern version with Java 11, our tested matrix is Eclipse 4.19, and we always take the two most recently released versions of Eclipse for our test matrix. At present, we're validating 4.24 and 4.25. Versions 4.20 through 4.23 are likely to work, but we no longer include them in our test matrix. So to wrap it all up, let's kind of connect all these and work our way in through the bottom. We start at the CUDA debugger interfaces. Those are internal interfaces that we provide within our runtime to allow debugging support for CUDA. On top of that, we have built our CUDA debugger API, which basically can be used for any program at all if it wants to act like a debugger to control and query the state of a running CUDA program. As we're demonstrating, CUDA GDB makes use of this CUDA debugger API. We happen to have third-party developers who also use the API, and it's fully available as source, and people can go ahead and use this debugger API if they want to do their own debugger development. Layered on top of this interface and layered on top of CUDA GDB, Nsight Eclipse, Visual Studio Code, and even, for example, one third-party developer who has done ARM Linero's Forge debugger, which works on top of CUDA GDB. So this integrated environment provides a very strong foundation for debugger development, consistent behavior between the tools, and consistent runtime performance. And it's available for use if you want to download and enjoy your own development exercises. Where to get all of this? So developer.nvidia.com tools overview provides a nice graphical display of the various tools and provides download capability. That finishes my section on the debugger, and now I'd like to hand off the presentation to Aurélien, who will talk about Compute Sanitizer in much greater detail. Aurélien, it's all yours.
So here, I am Aurélien Chartier, technical lead for the Compute Sanitizer tool. And here I want to talk about 5 new features we developed for the tools in the CUDA 11 timeframe. So to start with, the Compute Sanitizer is a collection of tools that help you to check correctness issues in your code via some sub-tools. Memcheck is our memory accessor and leak detection tool. RaceCheck allows you to detect shared memory data access hazards. InitCheck allows you to check for uninitialized device global memory accesses. And the SyncCheck tool detects thread synchronization hazards. You might know those tools in the CUDA Memcheck collection. The Compute Sanitizer was released in CUDA 11.0 to replace CUDA Memcheck tools, and as of CUDA 12.0, the CUDA Memcheck tools are now end of life. For the sanitizer, we also released an API that allows you to build third-party developer tools. So the first feature I wanted to talk is a feature we released in CUDA 11.3. And that allows you to do automatic padding of your memory allocation. Here I have some CUDA code that does a reduction on a vector. And as you can tell, there is an error in the code because we checked for inferior or equal to array size instead of strictly inferior, which means we'll have the last thread performing an illegal access. Unfortunately, if your input vector and your output vector are being allocated one after the other, it's possible they could be adjacent. And in this case, doing a off by one access in the input vector will just do an access in the output vector, which the tool will not be able to detect properly. So the compute center, the tool using the padding option, allow you to specify a given number of bytes that can be padded on each memory allocation. So in this case, that allows to insert a blank space between the input and the output vector, which makes the tool able to detect the out-of-bound access that is performed by the last thread. So next I want to discuss some ways of filtering which applications and kernel you want to sanitize in your application. So typically a workload can consist of multiple hundreds, if not thousands of different kernels, and it might be optimized to only sanitize a given subset of them. So first I want to discuss how to filter by kernel name using the dev-kernel option. So here we can specify a substring of which kernel we want to be sanitized. So here we are only interested in the Fibonacci kernels, which are being sanitized, but the matrix mirror kernel is being ignored by the compute sanitizer tool. We also have the reverse option dev-kernel exclude, and in this case we specify that we want to exclude matrix mirror kernels, so only the Fibonacci kernels are being sanitized. Note that those options were renamed in CUDA 11.4 to match the inside compute options, and the old names have been dropped as of CUDA 12.0. Next, we can also filter by kernel launch count. That's a new option that were introduced in CUDA 11.4. So the first one is launch count, where we specify the number of kernels we want to sanitize. And the second one is launch skip, where we specify the number of kernels we want to skip at the beginning of a given application. So in this example, we have 6 Fibonacci kernels, and we're going to skip the first 2, then sanitize 2 kernels, so the kernel launch 3 and 4, and then we're going to ignore the remaining kernels. Last is how to filter by process. So an interesting differences between CUDA Memcheck and CUDA Sanitizer in Compute Sanitizer is that in CUDA Memcheck, the tool was attaching to the very first process that was using CUDA. Compute Sanitizer behaves differently and will attach to the very first application that is being launched, regardless of if it uses CUDA or not. That might not be the case for a given workload that launches sub-processes using a script, such as the one we have for an example here. So in this case, we want to use the -target process all option in order to track all the sub-processes that are being launched by our script. That's a new option that was introduced in CUDA 11.0 update 1. In CUDA 11.6, we added another option, dev-target processes filter, to specify that only a subset of the sub-processes should be sanitized by the tool. Next, I want to talk about core dumps and how to do core dump and debugger integration. In CUDA Memcheck, the tool was directly embedded within the CUDA GDB tool. That is no longer the case with Compute Sanitizer, and instead we are leveraging the core dump feature that Steve was already as discussed previously. So here we have a simple example of a core dump demo test that is performing an out-of-band access. So we compile it with NVCC with no specific option other than the dash in order to get debug info. And then we can run it under the compute sanitizer using the dash generate core dump option. And automatically, upon encountering an error, the compute sanitizer will stop and generate a core dump file. Here it also specifies an example command line for CUDA GDB that can be used to load it into CUDA GDB. Upcoming in CUDA 12.2, we'll have an option so you can specify the core dump name. Here we use the CUDA GDB command line that was specified from the previous slide, and we can see that the core dump allows the application to be loaded in CUDA GDB. So one thing to notice is that only the threads that encountered an errors are present in the core dump file. That is why in this example, there are only 2 threads that are present in the core dump. The next option is CUDA malloc async APIs that were introduced in the CUDA 11 timeframe. In CUDA 11.7, we added detection for what we call the stream order races. So in this case, the pointer is, we allocate a buffer for pointers that is allocated on stream 1. And then we start using it right away on the second stream. That is not a correct behavior, as there might not be available in the second stream right away. So the correct pattern is to insert a synchronization event between the 2 streams that allows the CUDA driver to make sure that the pointer is valid in the stream 2. Similarly, when you perform a CUDA-free async, you want to make sure that the pointer is still not in use in other streams. In this example, this pointer is no longer valid on stream 2, as it is used after the last synchronization event made by CUDA device synchronize. Both those races can be detected using the -- track streamed order race option of the compute sanitizer tool. Lastly, the last feature I wanted to discuss is unused memory detection. That was a feature that was present on CUDA memcheck, but was not much advertised, so I wanted to discuss it here. So in this example, this code is allocating a buffer of 10 integers, but only use 8 of them, since we only have 8 threads. That might be a suboptimal pattern, and using the init check tool and the track unused memory option, we can detect that this allocation was not fully used, and here we also write the percentage of the allocation that was being unused. We also realize that that might be a pattern that is expected by your application, and in CUDA 12 we added a threshold option, so you can specify at which threshold the tool should start reporting unused memory buffers. So for example, in this case, if the unused memory threshold is 20, for 20%, the compute sanitizer tool would still report unused memory for this allocation. But if you use the 21, since the threshold is higher, the unused memory report will be silenced. So here you can find a list of other developer tools related session, labs, and connect with experts that you might be interested in. And for as a reminder, the developer tools are free and packaged in the latest version of the CUDA toolkit, which you can find at this download link. And we have support available on the forums. You can find more information at developer.nvidia.com, tools overview. Thank you for attending our talk about the CUDA correctness tools.